Does time really slow down in relativity? One of the key concepts in relativity is time dilation. In this video, we'll explore what really happens, whether time really slows down, and the consequences of relativistic speeds. These are the main claims for special relativity. The speed of light is constant for all frames of reference. Length contraction effects. Mass increases. Time dilation effects. Non-simultaneity of event. We'll just concentrate on these two to see how time dilation works. What does it mean by time slowing down? Is this like a movie that is played in slow motion? Do objects in motion experience a Twilight Zone-like environment where everything happens slower? Before we get into that, let's talk about the concept of heat and temperature, which will be key to understanding time dilation effects. What is the difference between an object that is cold and one that is hot? Is heat some kind of hot sauce or oil that gets into the molecules that makes them hot? Not quite. All the atoms or molecules of objects that are not at 0 degrees Kelvin are in a state of vibrating motion. The difference is just that the average momentum of a hot atom or molecule is greater than the one for a cold object. The higher the temperature, the higher the average momentum. When the temperature is very high, the momentum can be high enough for the atom or molecule to escape, which is what happens when water boils. Simple enough. Now let's go back to time dilation effects. To have a better understanding of what is going on, let's first build a simple clock. This clock is constructed with a magnet moving in a magnetic field, like the animation shown here. After an initial push, this magnet will oscillate between the two ends at a constant rate. We'll neglect friction effects and assume we are far away from gravitational fields. All clocks are based in something oscillating like this. This is essentially the definition of a clock. We are now going to accelerate this clock to, let's say, a final velocity of 1/2 the speed of light, where the Lorentz factor gamma is about 15%. Momentum is usually represented by the letter p, and it is the product of the mass times the velocity. We have changed the velocity, and therefore the momentum of the clock to the right, but the up and down momentum should remain the same. When we change the velocity to the right, relativity tells us that there will be a mass increase by a factor of 15%. Mass increases have been thoroughly verified in particle accelerators, so there is no doubt that this will happen. But now momentum conservation kicks in. If the mass increases by 15%, in order to keep momentum constant, then velocity has to decrease by a corresponding amount. This means that the magnet is moving slower. Still traveling the same distance, but at a slower velocity. You see how we have slowed down the clock, by the exact amount predicted by relativity, without slowing down time. Relativistic mass increases and good old Newtonian mechanics have slowed down the clock. The average momentum of all atoms and molecules is still the same, the temperature of the clock is still the same, but the increase of mass has forced a reduction in molecular velocities. This will slow down all processes, including the process that makes us age, all without slowing down time. Newton's time still ticks at the same rate. Relativity does not make any claims for changes on the strength of the magnetic field or electric charge, only mass. For an observer on Earth, events in a passing ship moving at high velocity will seem as if time is slowed down, but conservation of momentum still holds in all frames of reference. The temperature will still be the same for both the local and the external observer. This is the same as a spinning dancer extending their arms out. The change in the distribution of mass and conservation of angular momentum will make the dancer spin slower. This is what relativity calls time dilation effects. It should be obvious that there is no slowing down of time in either case. The change in mass and conservation of momentum will cause a change in velocity. If we want to insist that time also slows down regardless, then the math does not work. Now let's look at the claims for general relativity. General relativity claims the warping of space-time by massive bodies. No claims for length contraction. No claims for mass increases. Claims that space warping causes time dilation equal to the Lorentz factor using the escape velocity. Let's take the same clock we built before into a gravitational field. According to general relativity, the clock will slow down. In this case, it is because time actually runs slower. It really is like a Twilight Zone episode, or a movie played in slow motion, with different speeds at different altitudes. This type of event has some severe consequences. Let's say, for instance, that time slows down, as shown in this image. All events will occur slower. Without mass increases, there is a loss of momentum. temperatures are lower as measured by external observers. Since everything has to slow down, this includes the speed of gravity and orbital velocities. Kepler's laws would not work. The change in orbital velocities would impact special relativity time dilations. This part is not taken into account in the theory. Formulas for calculating time dilations do not include this effect. You can see that special relativity time dilations and general relativity time dilations are not the same. For special relativity, the object at high velocity itself experiences time dilation, but space around it is not affected. Light, even in close proximity to the object, still travels at the same speed. For general relativity, it is time in the space around a massive body that slows down. Objects are slowed down because time in the space surrounding them is slower. You can see we have two different explanations for what are essentially identical events. Now let's assume that gravity is the effect of space falling to Earth at the escape velocity, and that gravitational time dilations are special relativity effects due to our velocity relative to space as it falls to Earth. In that case, we can expect mass increases and conservation of momentum, just like the special relativity case. Temperatures remain constant, orbital velocities are not affected, and clocks slow down. You can see how this is a much better model for upholding the first law of thermodynamics. While we have shown that time does not slow down, clocks and all processes do. For all intents and purposes, it is the same as if time did slow down. Calling them time dilations is not an inappropriate name, but I hope you now understand what is really happening.